So it's a real pleasure to welcome Rudy in this seminar series. Rudy and I have known each other for a long time. I will not say how long, but it has been more than 10 years, let's say, notably. Okay, Rudy made his PhD at ETH Zurich. Your supervisor was Jürgen Linek at that time, and you got your PhD in '89. Then, after a postdoc, I think in USSR, you took a position in Heidelberg at the Max Planck Institute for Nuclear Physics, although you were not doing much nuclear physics at that time. I remember some very nice review papers from you on optical traps in particular, but you did very nice things there. And then you went to Innsbruck, where you are now still. In 2000, Rudy started in Innsbruck, started his own group there. He's professor of experimental physics at the University of Innsbruck. And since 2003, you are scientific director at IQOQI. IQOQI means Institute for Quantum Optics and Quantum Information, and this is an institute from the Austrian Academy of Science. So Rudy is known for many, many things in physics, in the physics of ultracold gases, both fermions and bosons. He's one of the rare experimentalists who have contributed equal importance in both fields. I will simply mention the BC of a molecule in a Fermi gas, the study of the BCS crossover, the observation of the pairing gap, which was really a very important thing. And on the Bose side, Rudy was the first one to condense cesium atoms. This is something that I know is difficult because I worked several years without success, and when Rudy finally reached the BC of cesium, I was really impressed that you could do that. And you did also marvelous things with cesium atoms. I described some of them in the lecture last year, I think, on Efimov physics. Rudy was the first one to observe Efimov states with 3 cesium atoms. So I'm really happy to have Rudy here with us today. And as the title says, he will speak about ultra-cold fermion mixture and Polaron physics, and also novel superfluids. Thank you, Rudy.
Yeah, thank you very much, Jean, for inviting me to this lecture here, to this seminar. And it's always great and very stimulating to visit Paris. And if I count correctly, it's my 4th seminar after a lecture at Collège de France starting in the 90s. And yes, you are right, 38 is larger than 10 years. Okay, it's really, really great pleasure for me. I wish I had more time for lab visits and so on. Maybe I should come back very soon. Okay, so this talk is about some recent developments in Fermi gases mainly, the Polaron problem, and also our quest for novel superfluids. And as Jean introduced already, I'm at 2 institutions, the University of Innsbruck and the Austrian Academy of Sciences, joining forces to establish a large center for quantum physics there. And now it is March 15, and at this time of the year, I'm always not sure which kind of background slide I should use. Here's the winter slide, but snow is slowly disappearing. Maybe I should switch to the spring slide here. Okay, so let me start with something you all know. We have the world of bosons and fermions, particles with integer spin and half integer spin, named after Bose and named after Fermi, bosons and fermions. And we all know that BEC, the Bose-Einstein condensation in a dilute gas, was achieved in 1995. And that was a starting point for fantastic developments and very exciting times that we were having in the lab, still having in the lab. With the fermions, or particles with half integer spin, the story is a little bit different, and there is this person here, very important, Wolfgang Pauli, with his Pauli exclusion principle, which tells you that you can only have 1 fermionic particle per quantum state. So it's a Pauli principle. And then you can argue maybe nothing dramatic would happen. I mean, here you have a Bose-Einstein condensate, but for the fermions, you just fill up all the quantum states up to a certain level, the Fermi energy, and that's it. Sounds a little bit boring. And that was an argument people had in the late 19th often. So fermions not so interesting, bosons are really interesting. But the situation with fermions is more subtle, and we know that there are macroscopic quantum states of fermions. And a very important point here is the interaction. So if you ask, is this interesting at all? Yeah, then an answer is, if you have interactions, strong interactions, that's very interesting and opens up really many interesting physics here. Good. So interaction makes them strong. How do we get strong interactions? First of all, we rely in almost all of the experiments on S-wave interactions. So we need, for the symmetry reasons, we need non-identical particles in the fermion world. And we do it with spin mixtures of fermions, usually in many experiments. Or we do it with species mixtures, and unlike particles because of their spin states, and here because it's just a different species with different masses. Okay, you can have S-wave scattering. And then a tool which also was mentioned in the lecture before, it's the Feshbach resonance, or the Fano-Feshbach resonance, one should call them. And so this is a typical Feshbach resonance where the function of the magnetic field, so the S-wave scattering diverges and gets very large, and in a certain region you get then really strong interactions. And the systems that we have in the lab are spin mixtures, and there we have lithium-6 spin mixtures, and well known in Paris, yeah, potassium-40 spin mixtures. And then on the species mixture side, we now have two interesting systems, and this is the potassium-40 lithium-6 mixture and the dysprosium-161 potassium-40 mixture, and I will report on results on both of these mixtures. Okay, so this is now the resonance, which is very important. And one thing which is always, I would say, a good friend in the fermion world. So normally, when we tune to strong interactions, then we have S-wave, where we have strong S-wave interaction. That means we also get fast free body decay. So three colliding particles, two form a dimer, the other one remains an atom and takes away the kinetic energy. This process can be super fast on resonance with a Bose gas. It's on the millisecond scale typically, or even faster, so the system decays rapidly. And you can use it as a probe. For example, we use this decay as a probe for Yefimov quantum states, but this is a different story. But for the fermions, if you are close to the resonance, this decay is usually suppressed. So Pauli says no. And this gives us long lifetimes, and this also leads to long lifetimes if you, for example, study dimer-dimer collisions. And it was shown in this paper here, very important paper in our field with Dima Petrov, Christoph Salomon, George Lapnikov, that they investigated the scattering of dimers and showed that there's a dimer-dimer scattering length which is on the order of the atomic scattering length, and they showed a strong suppression of inelastic decay in such a system. So let me summarize the key ingredients. We have mixtures of different fermions. We have tunable S-wave interaction. And we have close to a resonance collisional stability as a friend helping us. Good, so now let me look 20 years, a little bit more than 20 years back. A new quantum gas era started. And there was one experiment by the Thomas group at Duke University. They prepared a spin mixture of optically trapped lithium-6 atoms close to a Feshbach resonance and expanded through this cloud. And then they saw this here. They see a clear inversion of the aspect ratio. And this tells us that the expansion is no longer ballistic, it's hydrodynamic. In the BEC, so we interpret this as consequence of BEC formation, but in a strongly interacting Fermi gas, it's just classical hydrodynamics in this case, not really superfluidity. But it can form superfluids, and the expansion then looks very similar. And the second very early experiment on the strongly interacting Fermi gas is this experiment by the Salomon group, where they measured, as a function of the magnetic field across a broad resonance, they measured the interaction energy. And I think these are the first two experiments exploring the strongly interacting Fermi gas regime. Good. So then the Feshbach resonance, it's a fantastic tool also to create molecules. So the underlying a Feshbach resonance here is a molecular state which couples to the threshold. And this leads to the Feshbach resonance. And if you populate this molecular state, you create what we call Feshbach dimers, weakly bound molecules close to the threshold formed via a Feshbach resonance. And if you do it with fermions, two fermions together give us a boson. It's a bosonic molecule. Good. What else I want to say? I want to say, yes, this conversion of the atomic Fermi gas into a bosonic molecular gas was demonstrated in 4 experiments in 2003, now a little bit more than 20 years ago. And that was a fantastic starting point for further experiments. For example, then you can cool the molecules further and you can observe molecular Bose-Einstein condensation. Here's a gallery of early work on molecular Bose-Einstein condensation at Gila, in Innsbruck, at MIT, at the ENS, molecular Bose-Einstein condensates. A fantastic starting point to do more physics with the condensate. For example, to do BC-BCS crossover physics, the conversion by changing the scattering lengths from positive side to negative side, or vice versa. So the conversion between BC type system and the BCS type system. And this crossover has led to many, many interesting experiments, and I even not try to summarize the experiments, I just to point to this book with Willy Zwerger as the editor on the crossover physics and the unitary Fermi gas. The unitary Fermi gas is the Fermi gas with exactly resonant interactions on the resonance. And there's also a recent nice review article by Strinati and co-workers, Pieri, Rapkushuk, and Urban on the BC-BCS crossover, or BCS-BEC crossover physics. And it's still a very interesting topic, and I was delighted to see yesterday at the ENS the new experiment, new generation experiment on lithium-6, where they can do crossover for physics soon on the single particle level. Yeah, it's a new, still going on, producing exciting results. But I want to switch to a certain topic, which also started not 20 years ago, maybe 15 or 16 years ago. Normally, the experiment used 50-50 mixtures, equal number of spin states in lithium-6, for example. And it's very easy to introduce what we call population imbalance. We can investigate spin polarized Fermi gases. So we have, on this side, we have more blue than magenta ones, here more magenta than blue ones. So it's an imbalanced situation characterized by the polarization P of the system here. Good. And this is a new degree of freedom. And of course, you can bring it to the extreme. The extreme case then of an imbalanced system is a system with a single impurity in the bath of the other species here on one side and on the other side. That's the single impurity limit. And you can now address the many-body system in 2 ways. You can start with a 50-50 mixture and then move to one of the sides, see how what changes in the system, whether, for example, superfluidity breaks down. But the other approach is to start on the extreme limit with the polarons, with the impurities. Later we call them with interaction polarons, and change then the concentration of these impurities and see what happens then in the system. It's another approach to the many-body problem here. Good. So early experiments in 2006 by the Ketterle group and the Hewlett group looked at these imbalanced Fermi gases, and they saw a phase separation. You get a central component in the harmonic trap, which is superfluid, where the system is paired, and you get a polarized component outside. But it turned out a little bit later that this is not the complete story. There's a third region, and this is here in between, and this is where you have a majority of one species and a minority of the other one, and this forms the polaronic phase, and this is the fully polarized phase. And this was, for example, demonstrated in another experiment at the ENS, 2009 published, and they looked at the density profile here and see 3 different regions, the paired phase, I mean equal populations, the partially polarized phase, and the fully polarized phase. And that led actually this interest in these phases, when you find early papers, for example, also by Frédéric Chevy and the polarized Fermi gas, and others, and this problem then led really to the interest in the polaron physics. So already 15 years ago. And here's another experiment by the MIT group, led by Martin Svierlein, and they introduced polaron spectroscopy, creating a polaronic system and then driving within radio frequency the polaron into so the particle, the impurity, which forms the polaron into a non-interacting state, and then looking at the spectrum, and then they see different spectra at the molecular side. This is the molecular side, this is on the BCS side, and one of these, I think, is unitarity. We see a peak which signals the Polaron physics here, and this is the molecules there. Okay, so that's a brief history of the Polarons. And now let me switch to our labs. This is a photo from our lithium-potassium lab. And the current team looks like this. We recently had a generation change. I mean, the people who are now active in the lab are in the upper row here. This is now the PhD students, Rubens, Johanna, and Erich, postdoc Cosetta, and senior scientist Emil Kirillov. And these three ones, Isabella, Bo, and Adrian, they left last year or in the last 1.5 years and contributed a lot to the Polaron experiments here. Good. Impurities in the Fermi sea with strong interaction, the Fermi Polaron. We have a bath of fermions, the blue ones, and a few impurity atoms immersed into these fermionic baths. What are the main questions? You can divide it roughly into two classes. One class is the properties of individual quasi-particles, and the other one is the question about interactions. How do they interact with each other if the concentration gets larger? And the first question, I mean, we have been working on this for more than 10 years, and I think the main questions have been answered. Still some questions are left, but the main questions have been answered. And, but the interaction of the Polaron has been kind of not well investigated. There are some hints on that and some signatures, but there's still a lot of questions on how do these quasi-particles interact. And so let me come to this. Let me come to our experiment. So in a schematic view, we are using, this is a cross-beam optical dipole trap, standard 1064 nanometer infrared dipole trap, and we prepare a Fermi sea of lithium-6 atoms. Actually, here it's a single spin component. I mean, cooling and tone works in the usual way with 2 spin components, but then we kick out 1 spin component, and there's a Fermi sea of lithium-6 in a particular spin state, in most cases the lowest spin state left. And in this way, we create a Fermi sea of about 10 to the 5 atoms with T over Tf about 0.15. And then we can, okay, as I said already, we can create either a strongly interacting spin mixture, which can become superfluid, or just a single component Fermi gas. But now comes the impurities. And the impurities here in our experiments are potassium atoms. 10 to the 4 atoms typically, either potassium 40 or potassium 41. And the important difference is potassium 40 is a fermion and potassium 41 is a boson. Good. Now let me come, okay, then we apply a magnetic field and we can tune the interaction with of the impurities with the fermionic bath and see what's going on. Now I want to point to 3 important features which really help us in the experiments quite a lot. First one is the impurity cloud is much smaller than the Fermi sea. Why? 2 reasons. One reason is the potassium atoms are more than twice polarizable as compared to the lithium atoms, so the potential is stiffer. They are more confined. But the other reason is simply the Fermi pressure of the lithium-6 atom, which makes the cloud big, and this cloud is not degenerate, and it's much smaller. So the benefit is that the impurity atoms in the center of the trap see an almost homogeneous environment. So the variation typically is just a few % of the densities they see, so we get a homogeneous system for free in these experiments, which is very nice. Okay, so the other one that is a little bit more subtle, in the experiments we carried out recently, we want thermal impurities. We want to avoid degeneracy effects of the impurities. We can get degeneracy, we can condense the impurities so if they're bosonic. This is possible, but this causes complications. We want to keep them non-degenerate. But we want to have a deeply degenerate Fermi sea. So we can introduce a reduced temperature of the impurities, T over Tf impurity, which should be larger than 1, and T over Tf of the bath, which should be smaller than 0.1, let's say 0.1 typically. Then we put these conditions together, and we derive at the end, using the standard proportionality of the Fermi energy with the number density to the power of 2/3 over the mass, we can derive a condition for the maximum impurity concentration in the experiments to get these thermal impurity in the deeply degenerate Fermi sea. Then you see you have a quantity here, which is small, the reduced temperature of the bath over the reduced temperature of the impurities, and the quantity which can be big, the impurity mass over the mass of the bath atoms. And if you put in numbers, then we see in a spin mixture experiments, you have to stay well below, let's say, 3%, 0.03 concentration. Concentration is the local number density, ratio of the local number densities, to 3%, which is very hard to work at with a few percent of the particles. But if we take the mass of the potassium here, it gives us a large factor, and we can work with impurity concentration, let's say, up to 50%. This is an enormous difference and helps us a lot in the experiments. The second point, to summarize this slide, lithium potassium enables studies on the thermal impurities at high concentration. Okay, feature number 3, the Feshbach resonances. And there's a remarkable gift of nature. On this slide, if you look very, very carefully, you see it's not one red line, there's also a green line. These are two different Feshbach resonances. One is in the potassium 40, lithium 6 combination, the red one, and the green one is in the combination of bosonic potassium 41 and lithium 6. So the resonances, they are different magnetic fields, but we don't care about the particular magnetic field. But the width and also the background scatterings is almost identical within a few percent. So there are almost identical Feshbach resonances in these systems, and that means we can, in the experiment, by just changing the isotope and changing a little bit things in the cooling protocol and so on, we can switch from fermionic to bosonic samples under the same conditions. So to illustrate this, we have a kind of a switch on the experiment where we can say we want to work with the fermionic switch or the bosonic impurities and compare directly what happens there without other complications. And that's a very, very nice feature. Okay, good. So now let me come to the way we do spectroscopy, and it's a very simple, standard way, the so-called injection spectroscopy. We start with an impurity state, impurity in a non- or a weakly interacting state. So for all practical purposes, non-interacting, and we drive the impurity using a radio frequency into an interacting or strongly interacting state, which is Feshbach tunable. And we map out in this way, by radio frequency transfer versus radio frequency, the spectral function of the strongly interacting system by what is called, established in the field as injection spectroscopy. Some details, we work with pi pulses usually. So we set the pulse to pi pulse condition without interaction. Then we get a maximum signal. We use 1 millisecond Blackman pulses, and we have a spectral resolution which corresponds to about 4% of the Fermi energy. Good. Now this is actually one of our very first Polaron spectra, taken now probably almost 14 years ago, published here. And you see that near the Feshbach resonance, there is, on the lower side where the scattering angle is positive, there is an upshift of the energy of the particle. Here's a downshift. Far away from the resonance, you can simply describe it by a mean field, but here it already shows significant deviations. And closer to resonance, situation becomes more complicated, spectrum gets very broad, and in this spectra we didn't resolve anything. But this is our first spectrum, and we always present spectra in a way that we normalize energy to the Fermi energy of the medium, and we introduce a dimensionless interaction parameter, which is 1 over kf. Kf is the Fermi wave number of the medium. That's always the way we represent it. And the strongly interacting regime is roughly between -1 and +1. Good. So, and typical spectra look like this. If we cut through this image here and there, we see a spectrum of the repulsive polaron, where there's a peak, the polaron peak, the quasi-particle peak, and there's a broad spectrum of excitation with the width roughly of the Fermi energy of the medium. If we do it on the other side, you see the polaron peak of the attractive polaron, negative energies, and this tail of broadband excitations, which is the incoherent part of the polaron. But in most experiments, we are just interested in where is the polaron peak, and we investigate the peak position carefully. Okay, this was the starting point of many investigations, which I cannot summarize all here. But I want to point out, okay, we still have a nice collaboration with Pietro Massignan and Georg Brun, long-standing collaboration on the Polaron problem. They provided us with a theory based on a T-matrix approach and single particle hole excitations, considering like the famous Chevy ansatz. And you see it fits very nicely, and we can describe the Polaron spectrum in this way. And between the dashed lines, there's the spectrum is dominated by molecular excitations. Okay, but I cannot summarize all our work on Polarons here. We looked into various ways of doing spectroscopy, using a strong coherent drive, driving Rabi oscillations, and the Rabi oscillations give us a measure for the quasi-particle residue. You find it here. We introduced the Ramsey spectroscopy with 2 pulses, and this is an interferometric approach in the time domain, where we could investigate the Polaron formation. And we looked more recently into bosonic impurities, which can form a BEC, which gives an additional peak in the spectrum. But this is not the story today. But we, here in these experiments, we came across with the question of, are there mediated interaction? What happens if we have a higher concentration? And that's something which was driving our research in the last, let's say, 2 or 3 years, the quest for mediated interaction. And that's actually now the story. 2 important questions in context with the Fermi Polaron. How do Polarons interact with each other? And the second question is, what is the effect of the impurity quantum statistics? The Fermi Polaron means that the medium, the bath, is fermionic. But the impurities can be bosonic or fermionic. And we have the option to investigate both. Good. Then you find the answer in this paper, on the next short version in the next slides. There's a relatively simple prediction coming from Fermi liquid theory. You find it in a paper by Yu and Pethick from 2012. And the prediction is pretty simple. So if you look at the interaction energy normalized to the Fermi energy, you can write it in this way. What does it mean? C is the impurity concentration. Delta N is the number of atoms in the dressing cloud. So whether the impurity attracts particles from the medium and increases the local density or decreases it. And you see it's delta N squared. So the sign doesn't matter. Whether you repel or attract the particles from the bath does not matter here. And there's a prefactor and there's a sign. And the sign tells us it's negative for bosons and repulsive for the fermions. No, it's attractive for the bosons, plus is for the bosons, and minus is for the fermions. So these are the key predictions from Fermi liquid theory. Rather simple, and we are interested actually in this factor here, this 2/3, this minus plus some factor delta N squared, and this is what we call S. You will see that S stands for slope in the spectra. So we want to see whether we can reproduce this in the experiment. We can test this simple prediction here. Good, so how do we do this? Yeah, we investigate the Polaron spectrum with impurities with variable concentration. And here you see what we would expect according to the formula presented before for a relatively large concentration of 0.5. And you see if you have fermionic impurities in the Fermi medium or bosonic impurities, the effect is relatively small, and realistically we work at less, 2 or 3 times less, so it's really a small effect we are looking at. So how do we do that? This is the same kind of Polaron spectroscopy I introduced before, looking at the Polaron peak. And then you see the difference between the blue and the orange curve is slightly different concentration. And you see there's a significant shift. It's small, but it's there and statistically significant. The spectroscopic signal reveals a small shift, and there's more attraction for larger concentration here in this system. This is done with the Fermi with bosonic impurities. And you do it now you vary the concentration in the large range. You take spectra like this, you analyze them, and then you plot as a function of the concentration the energy shift. And you see linear behavior fits to that, and you can extrapolate it to 0 here. That would be the single impurity limit, actually. So you see there seems to be a certain slope, and it's statistically significant. Okay, but now that's not all. We have to do this not at one interaction strength. We have to vary now the magnetic field and do these experiments for variable interaction strength. And here's now the result. So these are similar measurements done with I think, 20 different interaction strengths on both sides. And you see always that there's a certain slope with the magnetic field, with the concentration variation. Good. How do we analyze this? Okay, now this is what I want to say. This was for the bosonic impurities in the Fermi sea. But we also have the fermion impurities in the Fermi sea. And that means another set of measurements. And this takes, to be honest, this takes months to take these data. But the experiment is running nicely overnight, and we have the time to get all this data. And then at the end, what you see is this, you can investigate the single impurity limit by extrapolating to 0. If you extrapolate to 0, then you get this result of the single impurity limit as a function of interaction parameter. You see for bosonic impurities, red, and green for the bosonic impurities, or red for fermionic, blue, green for bosonic impurities. And you see there's no difference, but this was expected, because if you have a single impurity, the quantum statistical character of the impurity cannot matter. So it should be the same, and this is confirmed by this experiment. It's good to see. It's a nice benchmark for the experiment that it makes sense. But now let me come to the slope. The slope, now, if we extract the slope, it looks like this. So we have the red points, again, for fermionic impurities. And you see on both sides of the Feshbach resonance, there is a certain upshift. For the bosonic impurities, on both sides of the resonance, there is a downshift. And that is exactly what was expected. The signs should not depend on the sign of the interparticle interaction scattering length. No dependence here. But it should depend on the quantum statistics. So I think these measurements confirm the basic predictions of this Fermi liquid model introduced by Yu and Pesek now in 2012 and brought to us by actually Georg Bohn. And so that's nicely confirmed. Sign same on the attractive and repulsive side, sign reversal with quantum statistics. The magnitude effect, I mean, there's no fitting. It's just as the theory would predict, there's no fit parameter. Okay, quite noisy data, but statistically significant. We see this, can confirm this effect. But this is only a certain subset of our data which avoids the strongly resonant regime. So you see the interaction parameter, the modulus of the interaction parameter is larger than 1. If we get closer to resonance, the situation gets much more complicated. And we see strong effects in the experimental data. We see on the molecular side here, we see upshifts for the green ones, the bosonic impurities, downshift for the red ones. On the other side, we see strong downshift in both cases. And we don't fully understand what is going on. We have some hints by theory provided to us by Georg, Pietro, and together with Miguel. We have some strong hints that this is due to molecule formation. So if weakly bound molecules are formed by collisions here, then it changes the picture completely. And they managed just by introducing the molecules into their theory to explain what we see. But on the other side, the repulsive side, it's not clear there. The signal just goes that way for both for both cases. And we don't understand it, but probably it's just a breakdown of the Fermi liquid theory. The interaction gets too strong. I mean, Fermi liquid theory means you have some still some Polarons, some quasi-particle character, and incoherent spectrum of excitations. Then if these quasi-particle gets so weak that it almost disappears, probably the whole picture does not make any sense anymore. We don't know, but this is, I think, open question, or you can call it work in progress. Okay, so now that's the story on the interacting Polarons. What next? Now we are setting up a new generation of experiments, and one open question is actually what happens if the impurity atoms are in motion, if you move them, and for example, what happens then? And the typical velocity of the system is the Fermi speed of the bath, which is in our case about 44 millimeters per second. If you are way below this characteristic velocity, you would expect that the dressing cloud can follow. If you reach this velocity, you can expect naively the dressing cloud can no longer follow and the picture will change radically. That's what we want to investigate. A nice tool to do it is actually applying Raman pulses. So with Raman pulses between different spin states, we can in the counter-propagating case, we can impart momentum on them, and we can increase the momentum in units of 2h per k. And 2h per k is a velocity change of 26 millimeters per second. It's just half of the Fermi speed. Maybe it's already a little bit too much, but then you can use not counter-propagating, but Raman beams under a certain angle to do this. We demonstrated that it works. We can drive nice Rabi oscillation, and this is just a gallery of Rabi oscillations. We can now also drive very fast pi-half pulses and so on in these experiments. But what we did now recently is to check our impurity accelerator. We applied these Raman pulses, sequence of Raman pulses from both sides to the impurity cloud. And the nice thing, it's now the impurities have a completely different resonance line, so you can, in a species selective way, address the impurities without affecting the path. And we can give them the impurity cloud momentum of n times 2h per k. We did it now n up to 9, I think, 18h per k, but in principle we could do much more. So what do we observe then? So we give the impurities a kick, and then they are interact or not, depending on resonance condition with the medium. We turn off the trap and then let them fly freely. And if they get decelerated by interaction with impurity, we see that in the signals here. Okay, this is a measurement which shows the position of the impurity cloud after a certain time of flight for different numbers of photon momenta. So 0h per k means there's no momentum transfer, and that's the original position. And then these you see linearly increasing with units of 2h per k. You see the position changes of the cloud. But this is done away from the resonance. But if we now tune on resonance, what would you expect? You would expect increased collisions, interactions, and slowing down of the cloud. We should see that. But what is the role of the momentum then? Okay, here's the data. You see there's a deceleration signal, which gets stronger for more momentum, but which also shows a clear shift, an energy shift. Okay, the resonance shifts with momentum. So we clearly see a resonance shift with momentum, but then you can look into the textbook, and this is nothing really surprising. You find in many textbooks, also in Jean's notes somewhere, you found this formula on the cross-section as the imaginary part of the scattering amplitude, and there's a momentum-dependent shift, which can be written in that way. It's just a shift proportional to k squared, or you can say to the kinetic energy. And if we just take the known parameters of our Feshbach resonance and fit it to the data, we get this curve here, the experimental points on this curve. And actually, so this fits very well to what we expect from the resonance. If you think through it, then the information that it actually gives is, for the Feshbach resonance experts, the differential magnetic moment of the Feshbach resonance. And it is fully consistent with what we know from our Feshbach resonance, some molecular spectroscopy and things like that. But it's a nice benchmark, a nice test. It works nice, and it's fully consistent with literature. Now we have an interesting tool, and now we want to really vary the momentum in the sample and see what happens to the Polaron spectrum then. Good, but now let me switch to another story. Okay, so far I talked, or in the very beginning I talked about balanced fermionic mixtures, and then I said imbalance can be introduced by changing the polarization, more from one spin component, more from the other spin component. This is a way to introduce imbalance. But there is another kind of imbalance, and the other kind of imbalance is mass imbalance. So we can vary the mass of the particles, okay, and introduce a certain mass ratio. Of course, it's hard to do it continuously, but you have to use different combinations of fermions to reach certain mass ratios. And if you look into this problem then in more detail, you will find the most interesting region is here, where you have a majority of heavy particles. That's this region here. Why? What happens there? Okay, here is a phase diagram from, I think, 2010 by Henk Stoof's group. And it shows a phase diagram of the regions we would expect here. Here's the polarization. Actually, this considers a homogeneous system, I should say, on top of the resonance, a unitary homogeneous system. And then you get, for zero polarization, zero temperature, you get a superfluid. Superfluid disappears here at the critical temperature, and you get the normal phase. Okay, if you introduce a certain polarization, then you get FR, and FR is not a Feshbach resonance, not a Farnell resonance. It is forbidden region. FR means it's a region where the system is expected to phase separate. So paired particles separate from unpaired particles. That had been observed also in experiments. Okay, here is a TCP, is a tricritical point on both sides, of course, for symmetry reasons. But now if we do the same with mass imbalance, we break the symmetry of the problem. And it's not the same whether I have positive or negative P. It looks now like this. Here's the majority of light atoms. And here's the majority of heavy atoms. Majority of light atoms, it looks qualitatively the same. There's this tricritical point. Nothing new happens. And, but here on the other side, there is an LP, which is a Lifshitz point. And that's where normal zero momentum Cooper pairs are expected to become unstable towards finite momentum pairing effects. And SS stands in this graph, should stand for supersolid. These are symmetry breaking phases. We now say these are full de Ferrel-Lakinov-Chinikov phases below this Lifshitz point. No one can make I think, an exact calculation of this or a very good prediction, but it's here the interesting things happen around this point here. And now this is now the quest for exotic phases in this system. And the point is, while some exotic phases have been predicted out for the mass balanced case, but for temperatures which are super low, let's say Fermi temperature over 100 or 1000. And I think no one really wants to do experiments on the lithium-6 gas with T over Tf of 1000, 1 over 1000. It's not the temperatures we reach. But if you here look at the temperature scale, it's not 1 over 1000, it's something like a little bit less than 20%. So here, interesting things happen in a region that we can reach in experiments. That's the main point. Okay, here the interesting stuff is expected to happen. So that was the main motivation for us to start experiments. It was an early motivation already 15 years ago to start the lithium-potassium activities. But it turned out that lithium-potassium has nice Feshbach resonances for Polaron physics, but not good Feshbach resonance for superfluidity. They are too narrow and not in the lowest spin channel, so this introduces losses and makes it not very well suited. But then the era of these heavy magnetic, strongly magnetic heavy lanthanide atoms started, and these also offered new fermions. They are fermionic isotopes, and we decided to set up a new experiment which combines potassium fermions and dysprosium fermions. The mass balance is, this is 40, this is 161, so it's roughly 4, the mass ratio, which is good, which is a reasonable mass ratio. You don't want to have it too big, because then you can have, again, unstable behavior because of Yefimov states and these things. So 4 is a good mass ratio, and there are certain other criteria for the experiment which I don't want to list here all, but therefore we decided for potassium dysprosium. Actually in Florence, they have a group of Matteo Saccanti, they have a nice experiment on lithium chromium mixtures, which has a higher mass ratio of 8, but which has similar ideas than we have. Good, so about dysprosium potassium, first of all, the team. This is the upper row is the present team, and then we have 2 team members who left the course of the last year. They have contributed a lot to the things I want to explain to you now. And at the moment we have 2 interns, Viviana and Charlotte. Charlotte comes from Paris actually and joined us recently. Okay, and Luc also came from Paris, he's a postdoc. Chunkit from Hong Kong and Alberto from Italy. Good, what else? The rest of this, how much time is left? Okay. When did we start?
15, so we have 20 minutes.
Okay, that should be okay. The rest of this talk, I want to touch a few topics. First of all, how to create the degenerate mixtures. This will be done very quickly. The question of interaction tuning. Will we find Feshbach resonances? Hydrodynamic behavior, observation of hydrodynamic behavior, molecule formation, and as a last slide, a very exciting new observation which we don't understand. Good. So, how do we create the super cold sample? Actually, it turns out this part is very easy with the potassium dysprosium mixture. So we have to consider that the optical potential is typically a factor of 3 times deeper for potassium atoms than it's for dysprosium atoms. Depends on the particular infrared wavelengths, but roughly a factor of 3. Okay, then we have the effect of gravity. And if we ramp down the power of the trap, then we will evaporate the dysprosium atoms, but we don't lose the potassium atoms. They stay trapped and are just sympathetically cooled. Evaporation of fermionic dysprosium works remarkably well. And here the dipolar character is very important because the dipolar character gives us universal dipolar collisions. So S-wave collisions do not freeze out at low temperatures as in other systems. We have at low, in the limit of low temperatures or low collision energies, you just get a finite cross-section, and it's typically on the size of, let's say, the rubidium elastic scattering cross-section. So we can very nicely evaporatively cool the single spin component of dysprosium and cool potassium-40 sympathetically. So we do this at low field for reasons of that there are many resonances of dysprosium alone, narrow Feshbach resonances, and you have to find a good spot to do this. But if you have to know the good spot, it works extremely well. Good, so and then we see double degeneracy of both species. With the dysprosium, we are a little bit higher than TF than 0.1. With potassium, probably we cannot even measure if it's thermalized even a little bit below. And we can control the number ratio of the particles by just changing the loading conditions in the trap. Good, so key question, and there was a question we were asking ourselves many years ago, would we find a nice interaction control knob? So the magnetic field to change and tune the interaction in a nicely controllable way. Do Feshbach resonances exist in the mixture, and can we use them for the experiments? And that started a long story, which I want to make short, just to present the main results. So we found a broad resonance at 217 Gauss, all in the lowest spin channel, at 217 Gauss, which is rather broad, but it's an overlapping scenarios of 3 broader resonances, the broadest one at 217. We characterized the resonances, and it's a nice tool for interaction tuning, definitely, but also has some problems. The problems are that this resonance region is contaminated by many narrow resonances of dysprosium alone and also of potassium of the mixture. So it's not so easy to ramp across the resonance because you produce, let's say, molecules on all these narrow resonances, and you have to find the right ramping sequence, which is a bit complicated to do these experiments. But then we were looking for other resonances, and to our surprise, we found a bunch of low-field resonances. And the most interesting one is not at 217 Gauss, it's at 7.3 Gauss, roughly. And this is the resonance here. And it's sufficiently broad for controlled interaction tuning, offers a significant universal range, and it's a fantastic tool. You have to control the magnetic field on the milligauss level, but if you have to do it at 7.3 Gauss, it's not such a big deal as doing it at a few hundred Gauss. So it's a wonderful tool that we found, and all the experiments, most of the experiments I'm reporting now on have been done on this resonance. Okay, so resonant interaction. This is a way to characterize the resonance, the standard measurements. This is just a thermalization measurement. We create the thermalized mixture, then heat up selectively one component, the potassium, from 100 to 500 nanokelvin, and then we wait for a certain hold time at a given magnetic field, and then we observe on resonance the fast thermalization within a few milliseconds here. This is a way to characterize the resonance by elastic scattering. And this is a measurement of the molecular state lying below the resonance. We can also carry out magnetic moment spectroscopy. And why do I show this? It's actually not so easy, not easy. No one has a good model to describe all these resonances. So we have to rely on purely experimental means to understand and characterize our resonances. But it has all the character of S-wave resonances, the right behavior of the binding energy, and the right thermalization behavior. So this is a fantastic resonance. Good. The first experiment we did now a couple of years ago, we created the mixture close to degeneracy, still in the thermal regime, and then just released it from the trap, looking at time of flight. Okay, in the thermal case, what you would expect is that the potassium atoms are 4 times lighter, and they should expand 2 times faster, therefore. That's what we see in the experiments. After the certain expansion time, I think of 8 milliseconds, you have a smaller dysprosium cloud, a larger potassium cloud, and there's a factor of 2 in the width. But now a little change in the experiments, little change, that before expanding the mixture, we jump on resonance on top of the resonance and have strong interaction. And then the picture drastically changes. For the dysprosium, it looks almost the same. There are 4 times more, not 4, but 3 to 4 times more potassium atoms. In this experiment, 2.5 times, okay. But we have more dysprosium atoms. The cloud stays almost the same, but the potassium cloud, it's much smaller now in the expansion. So the interaction leads to an expansion which is almost the same for both species. So what happens, we look into the profile into more detail. So we interpret this as a locked hydrodynamic expansion. We look into the profiles in more detail, and then we see something quite exciting. We see there's a core distribution of potassium which has the size of the dysprosium distribution, but there are side wings. And this kind of bimodality in a spin mixture was a clear signature for superfluid behavior. But we are taught, I mean, above the Fermi temperature superfluid, this cannot happen. This must be something else. Okay, no superfluidity. It's a generic effect of collisional hydrodynamics in a mass imbalance mixture. So what happens is that the lighter particles, they form kind of a Brownian motion in the core of the heavy particles. And sometimes they reach the outer region of the cloud. And if they reach the outer region, they can escape. And then they have the normal thermal velocities, and then the thermal expansion. And this explains the wing, and we can model it just in Monte Carlo simulations. Okay, but hydrodynamic behavior, the story goes on. Recently, we looked into dipole modes. I mean, here is a simple sloshing mode. I mean, if the dysprosium cloud here is not in the center of the trap, but a little bit outside of the center, we'll start to perform sloshing oscillations. What if we do it with 2 species? Okay, here we have the potassium species, and it also starts to slosh, but it will slosh at a largely different frequency. There's a factor of 3 between the frequencies. But what you expect, there's some kind of interaction between the clouds, which you may characterize just as a friction effect. Okay, so and we carried out these experiments. There are 2 interactions which are taking place, just a collisional dissipation, it's a friction effect, damping of the relative motion, but there's also a mean field attraction or repulsion between both clouds. Both effects are there. Now you can set up a simple model. You can say it's based on a linearized Boltzmann equation. You can also say it's just a phenomenological approach. Coupled differential equations where you have the oscillation term, so the force acting on one cloud. M1 is the total mass of the dysprosium cloud. The part from the harmonic trap here, which causes oscillations. Here's a friction term proportional to the difference in the velocities. And here's the reactive term, which is characterized as attractive or repulsive interaction. Actually, this model is nothing new. You find it in the literature, published in 2001 by Gensemer and Jin. They were looking at 2 different spin components in a magnetic trap, performing a coupled motion also by the Florence group, Ferlaino and co-workers for the rubidium potassium mixtures. You find this model, and you find this model then also in an extended version together with this coupling term here in 2 other theoretical papers a little bit later. And I should also say this model was also applied to the mixed lithium-6 and lithium-7 superfluids in the ENS experiments. Okay, so what are the predictions of the model? Now let me forget about the reactive interaction. Let me just look at the friction effect. Then you see if there's no very low friction, you have the independent modes. If you increase the interaction, these independent modes change a little bit their frequency, okay, and the damping increases. But then something dramatic happens. One mode disappears completely, and the other mode experiences a stronger frequency shift. So we call this mode the dysprosium crossover mode because it connects to the bare dysprosium oscillation at 0 interaction. We call this the potassium mode, and this disappears completely in the overdamped regime. But if you look at the damping, you see something else happening. If this mode disappears, you see it here, the mode disappears, you see that it splits into two exponential damping modes. There's no more oscillation, it's just exponential damping. It's very typical to an overdamped oscillation or overdamped harmonic oscillator. And there's a second mode, the dysprosium crossover mode, which has weak damping here, increasing damping reaches a maximum, and then in this very strongly damped case where the two components oscillate together, there's also the damping gets much weaker. Okay, this is very rich, what you can do there. I just want to show two examples. And here you see what happens to the oscillation of both components, the blue, the dysprosium, the orange one for potassium. You see the large frequency difference if you increase the friction here. Then you see the dysprosium gets some damping. You see a second frequency component here emerging. Dysprosium damping gets even stronger. But if you have a very strong, this is unitary interaction, then you see the oscillation is almost the same and the damping is much weaker. This is what you expect here. With the damping goes down again in this locked hydrodynamic regime. And this is very similar, this locking effect, to the observation of the mixed superfluids in lithium-6, lithium-7 systems actually observed here. But in their case, the difference in the frequencies of the bare frequency is 10%, whereas in our case, it's a factor of 3. So it's much harder to lock these oscillations. You need much more dispersive coupling, friction coupling. Okay, this is some more data I want to show. We can measure the frequency and damping across the resonance. This is the resonant case, and we can model it with our model, and we fit it. We can fit the parameters characterizing friction and reactive coupling, and you see, we can get everything. We fit it to frequency and damping, and with these parameters we get predictions for the relative phase and for the relative amplitude. And I just want to point to this asymmetry. There's a slight asymmetry here in the profile, and a slight asymmetry in the damping, a slight more pronounced asymmetry in the phase. And this is the reactive effect. It's very weak. If you have no reactive effect, then no mean field attraction or repulsion, then the asymmetry disappears, but the structure looks quite the same. So this coupling constant K has a weak effect, but it can be observed. But now, the last thing I want to show here related to this damping is friction. How to characterize now the friction in the, let's say, close to the resonance and unitary regime. And we introduced a microscopic friction coefficient, which is actually connects the local force density with the product of the two number densities. And this is, I think, the best quantity to express the local friction. And we can measure this coefficient with different modes, actually. And on resonance, you have these gray points, and this is from the fast damping mode. There's a very fast exponential damping mode. This is the relative motion of the two components, which is then very rapidly damped. And this is damping on the millisecond timescale. And this is the best quantity to extract this friction coefficient. Why? Because if you look at longer oscillations over, let's say, 100 milliseconds, you have some heating effects, you have some losses, and things which make it a bit more complicated. But this is so fast, millisecond, that nothing bad happens, and you have the pure effect of friction, and you can very nicely extract the data there. And I think this is interesting to look at this universal friction coefficient here at the center. We have some preliminary comparison with MIT data on similar experiments on spin mixtures, and this fits nicely together, but we have to analyze it more carefully. This is work in progress. So what else? Let me again look 20 years back. We had the hydrodynamic behavior of the fermion systems as a very important signature of interesting behavior, and then the molecule formation. How about molecules in our case? So hydrodynamic, we have molecules. How about the molecules? What is the present status? Okay, so this is now an image where we produced Feshbach molecules just by ramping across the resonance. And this ramp produces then, converts a part of the atoms into Feshbach molecules, and the other part remains free atoms. And then we do the usual Stern-Gerlach separation in a way that we tune a levitation gradient, which holds the atoms against gravities, and such that the molecular cloud stays at the same level. This is the right levitation for the molecular cloud. For dysprosium, we have this enormous magnetic moment of 10 UB, and they are easily over-levitated. Even they are heavy, but the magnetic moment is so large that they are over-levitated, and they are accelerated upwards by the magnetic gradient. Potassium atoms with 1 UB don't have enough levitation gradient, they fall downwards. So this is the separation into 3 components: dysprosium atoms, potassium atoms, and the DYK molecules levitated. Okay, and this is very similar, analogous to the early experiments on potassium dimers, where these are the 2 different spin states, and this is the molecular cloud. Good. Now we can do the same experiment. Here, this was done in free flight after release from the trap. We can do it with a weak trap still on. Dysprosium atoms and potassium atoms are drawn out of the trap immediately, and dysprosium stays trapped. So here, similar picture, but with dysprosium kept in the trap. And then we have a trapped sample of pure Feshbach dimers of DYK. They should be bosonic. Now it's interesting, what is the lifetime? What is the temperature? What is the phase space density? So we do thermometry, just time of flight of the molecules, and we see that the molecular cloud has a temperature. So we believe in the horizontal measurements, because vertically there are additional excitations of 45 nanokelvin. And from the trap and the number of atoms, we calculate the phase space density, which should be around 0.14. And now we have improved the experiment. We have a better conversion, better conditions. So we are approaching 1 in the experiments on these Feshbach molecules, and pretty close to degeneracy. And now, but the other question is about losses. Losses induced by, we see that the sample decays in the trap typically on the 10 or 20 millisecond time scale. And the time constant of the decay depends a little bit on the magnetic field, the tuning from resonance. So what is going on? Actually, these curves show us this is purely exponential decay. This is not a collisional effect. Collisions are not the problem. That's the good news. Collisions are not the problem in elastic collisions. We apparently benefit from this Pauli suppression effect. Something else. And something else turns out to be light-induced decay. And this is actually what I want to show before discussing the light-induced decay. We see that the lifetime changes with the magnetic detuning. If we get closer to resonance, the lifetime increases, here up to 25 or 22, 23 milliseconds. Why does the lifetime depend on the magnetic detuning? So our idea was, and that has been seen also in other experiments, that the closed channel fraction, the molecular part of the wave function, that couples to something else, is coupled by the trap light, and that leads to losses. And here, closer to resonance, the closed channel fraction decreases and decreases, therefore loss also decreases and lifetime increases. Okay, the explanation is that we have light-induced losses. And here are just the atomic states, ground state plus ground state plus excited state of the 2 atoms. But below, there's a continuum, or I would say a very large density of molecular states. In particular, in these complicated systems, you have not only 2 molecular potential curves, you have 10, and you have enormous complicated coupling. So you have an enormous density of different molecular states. So what probably happens, we're quite sure about this, we excite from our colliding atoms, we excite something in this molecular structure, which can be very broad, and that leads to decay into the continuum of molecules or molecular states here. In the end, it's just a loss mechanism. And so how can we improve? We can tune, actually we can try another laser, and by changing the trapping laser from near-infrared 1064 nanometer to 1547 nanometer, another telecom fiber laser, we could improve the lifetime by a factor of 3 already. And that's one point. And also we can do a little bit of spectroscopy, scanning over 1 nanometer, and we also see clear resonances which indicate resonant excited molecular state. So the good news, we are not limited by collisional decay, but we have this trap light induced decay. We have to do something against it. Tuning closer to resonance and maybe using laser light even more detuned. We are thinking now about using laser light in the 2 micron region, which is not so trivial. Good, so 2 problems, maybe 2 solutions, trap light induced losses and magnetic. Okay, skipped the second part, magnetic anti-trapping. This is a complication that comes from the curvature of the magnetic field in the levitation field and leads to some magnetic anti-trapping effect. So it limits us. We cannot get very close to the resonance center. But what can we do? Solution is we can go far into the infrared, 1547 at the moment, maybe 2 micron in the future. And the magnetic anti-trapping comes from the levitation gradient. We can replace our dipole trap with a 1D lattice, and we can rid of the levitation gradient and work with a homogeneous magnetic field. So the trap scheme we have now in the lab looks like this. We have a 1D lattice, which confines our atoms and molecules. We produce the molecules there. And this solves the problem here of this magnetic anti-trapping. And also here we have a significant improvement. We are approaching lifetimes of 100 milliseconds. And then we load the sample, do some evaporative cooling, and expand the sample then. And want to measure the temperature. And there we see something bizarre. We see this here. So these are different time of flight pictures and profiles for different depths of the evaporative cooling. This is deep evaporative cooling, this is less deep evaporative cooling. And we see a bimodality. There's about 50% component are here in this broader component, and the rest is in the more narrow component. And the deeper we go in the evaporative cooling, the more the central fraction increases. Now you might say, oh, well, this looks like Bose-Einstein condensation. Perhaps it is, yeah, but we don't know. It's a complicated situation in the lattice, and it could be something else. We still have some ideas what we have to check. And I think my role is now to play devil's advocate and find alternative explanation, which is not Bose-Einstein condensation. We see what will come out of it. I mean, the conditions are close to Bose-Einstein condensation, but how we do it at the end, okay, it's an interesting point. Okay, and with that, I think I'm finished. And just want to summarize. I mean, I looked 20 years back, the milestones in the field of strongly interacting Fermi gases. We are now in a similar situation with the species mixtures. We have hydrodynamic, deep hydrodynamic behavior, which is only possible with these fermionic systems and their stability. We have molecules. We are close to degeneracy. Let's see what the future will bring. And just a very general conclusion. Ultracold fermion mixtures, I hope I could convince you that this is a great playground for physics of strongly interacting many-body systems and offers many opportunities and challenges for future experiment and theory. With that, I conclude and thank you all for your attention. Thank you.